Picture a journey that begins at the edge of the Milky Way and continues in a straight line for 330 million light-years. For the first stretch, the view outside your window would look familiar. Galaxies scattered like grains of sand, some alone, some gathered into loose clusters, all of them tracing the faint threads of what astronomers call the cosmic web. Then, somewhere past the constellation Boötes, the herdsman, the galaxies begin to thin out. Fewer clusters, fewer stray spirals, fewer points of light at all. Eventually there is almost nothing left to see. And that emptiness does not end after a few million light years, the way it might around an ordinary underdense patch of sky. It keeps going and going for hundreds of millions of light years more, until you have crossed a region of space so large that if our own galaxy sat at its very center, humanity would not have discovered the existence of any other galaxy until the middle of the 20th century. This region is real. It is called the Boötes void, and it remains one of the largest structures of its kind ever mapped. Discovering a hole in the universe was, in its own way, an accident. In 1981, the astronomer Robert Kirshner and his colleagues were conducting a survey of galaxy redshifts, a technique that measures how the light from distant galaxies has been stretched by the expansion of space, which in turn reveals how far away those galaxies are and how they are distributed in 3 dimensions rather than just as flat points on the sky. Redshift surveys were still a relatively young tool at the time, and astronomers were using them to build the first real 3-dimensional maps of the nearby universe. As Kirshner's team plotted galaxy after galaxy, they expected to find the same rough pattern that shows up everywhere else in the observable cosmos. Matter clumped into filaments and clusters, separated by smaller underdense gaps. Instead, in the direction of Boötes, they found a conspicuous absence. Where they expected dozens of galaxies, they found almost none. The team joked, somewhat nervously, that they might have discovered a piece of the universe that space itself had forgotten to fill in. That first estimate placed the void at roughly 300 million light-years across, a number that was almost immediately difficult to reconcile with the physics of structure formation, as it was understood at the time. Later refinements adjusted the figure, with most modern measurements placing the void's diameter somewhere in the range of 250 to 330 million light-years, depending on the precise boundary used and the survey doing the measuring. Even taking the more conservative end of that range, the Boötes void is enormous. For comparison, the entire local group, the collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller companions, spans only about 10 million light-years. You could fit the local group inside the Boötes void more than 20 times over along a single straight line, with room to spare. To really appreciate why this discovery mattered, it helps to understand what astronomers mean when they talk about the cosmic web. On the largest scales, matter in the universe is not spread out evenly like fog. It is organized into a vast, foam-like structure. Galaxies and galaxy clusters sit along filaments, long thread-like structures made of dark matter and ordinary matter bound together by gravity. Those filaments intersect at dense nodes, where the richest galaxy clusters are found, and they enclose vast, relatively empty regions called voids. This structure did not appear randomly. It grew from tiny fluctuations in the density of the early universe. Fluctuations so small that in the cosmic microwave background, the afterglow of the Big Bang, they show up as variations in temperature of only a few parts in 100,000. Over billions of years, gravity amplified those tiny differences. Regions that started out very slightly denser than average pulled in more and more matter, eventually growing into the filaments and clusters we see today. Regions that started out very slightly less dense lost matter to their denser neighbors and slowly emptied out even further, becoming the great voids that now occupy most of the volume of the observable universe. This is the essential context for understanding the Boötes void. It is not a wound in space, and it is not evidence that the fundamental rules governing how galaxies form have broken down somewhere along the way. It is, in essence, an extreme example of a process that has been shaping the universe since almost the beginning of time. What makes it remarkable is not that it exists, but how large it is, and what its size can tell us about the limits of our models for how cosmic structure grows. If you want to feel the true scale of this place, consider light travel time. Light from the far side of the Boötes void, if there happened to be a galaxy there for it to originate from, would take roughly 330 million years to reach an observer on the near side. That is longer than the entire history of complex animal life on land. When the light we now receive from galaxies near the edge of the void first began its journey, on Earth, the supercontinent Pangaea was still tens of millions of years from forming, and the ancestors of dinosaurs had not yet appeared. The void has existed, in some form, for a length of time that dwarfs the entire span of multicellular life as we know it, and it has been slowly growing that entire time, the way all cosmic voids grow, through the gradual outward drift of galaxies, as gravity pulls them toward the denser walls that surround the emptiness. Before we go further, it is worth pausing on a small but important idea, one that becomes a recurring theme throughout the study of cosmic voids. Nothing about this region is actually a perfect vacuum in the way that term might suggest. Voids are underdense compared to the average density of the universe, not completely empty. The Boötes void contains a smattering of galaxies, drifting through the darkness like isolated campfires on an otherwise unlit plain. Early surveys found around 60 galaxies within its boundaries. That might sound like a reasonable number until you compare it to what you would expect in a region of ordinary space that size. A typical volume of the universe with the same dimensions as the Boötes void would be expected to contain somewhere in the range of 2,000 galaxies, based on the average density of galaxies observed elsewhere. Instead, astronomers find roughly 1/30th of that population, an emptiness on the order of 95% compared to the cosmic average. That comparison, expected galaxy counts against observed galaxy counts, sits at the very heart of why the Boötes void has occupied scientists for more than 4 decades. It forces a question that sounds almost philosophical, but is entirely a matter of physics. Is the universe as uniform as our best theories assume it to be? Or are there regions so extreme that they hint at gaps in our understanding of how matter organizes itself across cosmic history? That question deserves a careful answer, and answering it requires us to look closely at one of the oldest and most foundational assumptions in modern cosmology. The assumption in question is called the Cosmological Principle, and it is one of the quiet pillars holding up almost everything else in modern cosmology. In its simplest form, the Cosmological Principle states that on sufficiently large scales, the universe looks roughly the same no matter where you are standing, and roughly the same no matter which direction you look. Astronomers describe this with 2 words borrowed from geometry: homogeneous and isotropic. Homogeneous means uniform in composition from place to place. Isotropic means uniform in every direction. Together, these 2 properties imply that if you could zoom out far enough, the clumps and voids and filaments of the cosmic web would average out and the universe would appear smooth, like a fine-grained material that only reveals its texture up close. This is not an arbitrary assumption. It emerges naturally from Einstein's theory of general relativity, which becomes vastly simpler to solve if you assume homogeneity and isotropy, and it has been supported by an enormous body of observational evidence, particularly measurements of the cosmic microwave background, which appears remarkably uniform across the entire sky once its overall temperature and known deviations are accounted for. The cosmological principle is not just convenient bookkeeping. It underlies the standard model of cosmology, often referred to by the shorthand Lambda Cold Dark Matter, which combines a cosmological constant representing dark energy with cold dark matter to explain the expansion history and structure formation of the universe. If the cosmological principle was seriously wrong, a great deal of modern astrophysics would need to be rebuilt from the ground up. Here is where the Boötes void becomes genuinely interesting rather than simply strange. The cosmological principle is a statement about the universe on the largest scales, generally understood to apply once you are averaging over regions hundreds of millions of light years across or larger. Individual structures smaller than that, including galaxies, clusters, filaments, and voids, are expected to show considerable variation, precisely because that variation is what structure formation is supposed to produce. The real question is not whether voids exist. Voids are a completely normal, expected feature of the cosmic web. The real question is whether a void as large as the one found in Boötes can be explained by ordinary structure formation within the 13.8 billion year age of the universe, or whether its size pushes past what the standard model predicts is statistically likely. This is where the phrase mathematically impossible, which shows up in some popular accounts of the void, needs to be handled with care. It is not literally impossible for a void this size to form under standard cosmology. Computer simulations that model the growth of cosmic structure from the initial density fluctuations recorded in the cosmic microwave background do produce voids of comparable scale. Given enough time and the right initial conditions, what the Boötes void represents is something closer to a statistical outlier, an unusually large example drawn from the extreme tail of the distribution of void sizes that the standard model allows. Extreme outliers are not evidence that a model is broken. Every statistical distribution has a tail, and somewhere in that tail sit the rarest, most extreme examples the process can produce. But extreme outliers are worth studying closely, because they test the limits of a model more rigorously than an average example ever could. And because if enough of them start appearing, or if they turn out to be even larger or more common than the standard model predicts, that would be a meaningful signal that something in our understanding of the early universe needs revision. Multiple independent groups of cosmologists have run large-scale structure simulations specifically to check whether a supervoid, the size of Boötes, is compatible with the standard cosmological model. The general consensus from these studies is that while such a void is rare, its existence does not require abandoning the cosmological principle or the broader framework of Lambda Cold Dark Matter cosmology. It sits at the edge of what the model predicts, not outside of it. This conclusion matters because it reframes the entire narrative around the void. It is not a crack in the foundation of physics. It is closer to a stress test, a natural experiment that the universe happened to run for us, and one that keeps astronomers honest about the limits of their models. That said, the presence of an extreme outlier does raise a legitimate scientific concern that is worth taking seriously rather than dismissing outright. Dark matter plays the leading role in structure formation according to the standard model. Ordinary matter, the atoms that make up stars, planets, and people, only accounts for around 5% of the total energy content of the universe. Dark matter, an invisible form of matter that interacts through gravity, but not through light, accounts for roughly 27%, with the remaining 68% attributed to dark energy, the mysterious force driving the accelerating expansion of the universe. In this framework, voids form because regions with slightly less dark matter than average fail to attract enough additional matter to keep pace with their denser surroundings, and they are gradually stretched even emptier by the differential pull of gravity toward the denser walls nearby. If the properties of dark matter, or the precise statistics of the initial density fluctuations left over from the earliest moments after the Big Bang, differ even slightly from current assumptions, the predicted frequency and size of extreme voids like Boötes would shift as well. In this sense, studying the void is really a way of using an enormous natural laboratory to test the fine details of dark matter physics, physics that remains fundamentally mysterious, even after decades of dedicated experiments designed to detect dark matter particles directly. There is also a second explanation worth taking seriously, one that does not require any new physics at all. Some cosmologists have pointed out that the apparent emptiness of a void depends heavily on how thoroughly astronomers have actually searched it. Galaxy surveys have historical biases. Early redshift surveys, including the one that discovered the Boötes void, were most sensitive to bright galaxies, the kind with vigorous star formation, lighting up large populations of hot blue stars. Dimmer, smaller, or more diffuse galaxies, the kind that might be expected to dominate a genuinely underdense region, are much harder to detect, especially at the distances involved. This raises an important possibility. Some of the apparent emptiness of the Boötes void might not reflect a true absence of galaxies, but rather a population of extremely faint galaxies that earlier generations of telescopes simply were not sensitive enough to find. Later, more sensitive surveys using improved detectors did find additional galaxies within the void's boundaries that earlier searches had missed, which lends some support to this idea, even as the void's overall underdensity, compared to the cosmic average, has remained a robust and repeatedly confirmed result. Taken together, these two threads, the statistical rarity implied by structure formation models and the observational limits of galaxy surveys, do not point toward a crisis in astrophysics. They point toward an active, ongoing area of research, one where a genuinely strange corner of the observable universe is being used to sharpen our understanding of both cosmological theory and the practical limits of the instruments we use to test it. If you find yourself wanting to sit with an idea like this for a while, that instinct is worth following. Voids like this one are strange enough that a single viewing rarely settles all the questions they raise, and it can help to return to a piece like this a second time once some of these numbers have had a chance to sink in. The handful of galaxies that do exist within the Boötes void are not scattered randomly. When researchers plotted their positions more carefully in the years following the initial discovery, a peculiar pattern emerged. Rather than being spread evenly throughout the void's volume, many of the known galaxies trace out a loose filament-like structure, a sparse chain running roughly through the middle of the void, sometimes described informally as a bridge of light crossing an ocean of darkness. This is not entirely surprising in light of what we already know about the cosmic web. Even within an underdense region, gravity still operates, still pulls matter together along the paths of least resistance, and still produces filamentary structures, just far weaker and far more sparsely populated than the filaments found in denser parts of the universe. The existence of this faint internal structure suggests that the Boötes void is not simply a featureless gap. It is closer to a miniature, diluted echo of the same cosmic web that organizes the rest of the universe, just stretched thin almost to the point of vanishing. The galaxies found within the void turn out to be scientifically valuable for a reason that goes beyond simple curiosity. Galaxy evolution is heavily influenced by environment. In dense clusters, galaxies frequently interact with their neighbors, merging, colliding, and stripping gas from one another through a combination of gravitational tidal forces and a process called ram pressure stripping, in which a galaxy moving through the hot, thin gas that fills a cluster has its own reservoir of star-forming gas physically pushed away, like wind blowing smoke out of an open window. These interactions tend to accelerate galaxy evolution, transforming gas-rich, actively star-forming spiral galaxies into quieter, gas-poor elliptical galaxies over a relatively short cosmic timescale. Galaxies inside deep voids experience almost none of this. With so few neighbors, and those neighbors typically located tens of millions of light-years away, rather than mere hundreds of thousands, void galaxies evolve in near-total isolation. Multiple observational studies of void galaxies, not limited to the Boötes void alone, but including similar research on other large voids identified across the sky, have found that these isolated galaxies tend to be bluer, meaning they contain a higher proportion of young, hot stars and richer in gas, meaning they retain more of the raw material needed to keep forming new stars, compared to galaxies of similar mass found in denser environments. In effect, void galaxies age more slowly, not because time passes differently for them, but because the environmental processes that typically accelerate galactic aging are almost entirely absent. This makes them extraordinarily useful as a kind of natural control group for galaxy evolution research. If you want to understand how much of a galaxy's transformation over cosmic history is driven by its surroundings, rather than by internal processes alone, comparing cluster galaxies to void galaxies offers one of the cleanest tests available. Some astronomers have described void galaxies as living closer to the conditions of the early universe than their counterparts elsewhere, not because they are literally younger in age, since most galaxies across the universe began forming stars at roughly similar cosmic epochs, but because their evolutionary path has been slowed and simplified by the absence of the disruptive interactions that reshape galaxies in busier neighborhoods. In that specific sense, calling them time capsules is a reasonable way to describe them, so long as it is understood as a statement about pace of evolution rather than a claim that they are somehow frozen relics untouched by 13 billion years of cosmic history. The question of what fills the space between those isolated galaxies is where the science becomes genuinely open-ended. Voids are underdense in galaxies, but that does not necessarily mean they are equally underdense in every form of matter. Ordinary matter, sometimes called baryonic matter to distinguish it from dark matter, does not always collect into visible galaxies. A significant fraction of the universe's ordinary matter is thought to exist in a diffuse, extremely hot and extremely low density state, sometimes referred to as the warm-hot intergalactic medium, spread thinly along filaments that are far too faint to detect through visible light alone. Some of this diffuse gas likely exists within voids as well, tracing out the same faint filamentary skeleton suggested by the loose chain of galaxies found within the Boötes void. Detecting this diffuse matter directly is extraordinarily difficult, since it does not glow the way stars do, and it is not dense enough to produce strong absorption features in the light of background objects, the way denser gas clouds can. Researchers have made progress using indirect techniques, including analyzing subtle distortions in the light from distant quasars that happens to pass through a void along its journey to Earth, and studying the gravitational lensing effect that even relatively small concentrations of mass can produce on the light of more distant background galaxies. These techniques remain at the frontier of observational astrophysics, and a complete inventory of exactly how much ordinary matter, dark matter, and diffuse gas exists within a void like Boötes is still an active area of investigation rather than a settled question. What can be said with confidence is that the void, while dramatically underdense compared to the cosmic average, is very unlikely to be a true vacuum in any strict sense. Even the emptiest large-scale structure the universe has to offer still carries some trace of the same material that built every star, planet, and galaxy elsewhere. Because the Boötes void sits at such an extreme edge of what standard structure formation predicts, it has attracted its share of more exotic explanations over the decades, some grounded in serious theoretical physics and others considerably further from the mainstream. It is worth walking through both kinds honestly, because separating real, testable hypotheses from speculation that cannot currently be tested is itself part of doing good science. On the more rigorous end, some cosmologists have explored whether extremely large voids could be connected to physics from the very earliest fractions of a second after the Big Bang, during a hypothesized period of extraordinarily rapid expansion called cosmic inflation. Inflation theory proposes that the universe underwent a burst of exponential expansion an incomprehensibly small fraction of a second after its birth, stretching quantum-scale fluctuations in the density of the early universe up to astronomical size. Those stretched fluctuations became the seeds for all future structure, the same seeds that, over billions of years, would grow into galaxy clusters on one end of the spectrum and voids on the other. Some inflationary models predict a nearly perfect, smooth spectrum of fluctuations, while other more complex models allow for rare, larger amplitude fluctuations that could, in principle, seed unusually large voids or unusually large clusters later in cosmic history. Under this framework, an object like the Boötes void would not represent a phase transition pushing matter away, in the dramatic sense that phrase might suggest, but rather the visible, billion-year-aged remnant of an unusually deep dip in the density of the universe, when it was less than a trillionth of a second old. This remains an area of active theoretical research, and while it is a genuinely serious line of inquiry, it has not yet been confirmed as the specific explanation for the Boötes void in particular, since distinguishing an inflation-seeded outlier from an outlier produced by ordinary statistical variance within standard structure formation is observationally very difficult with current data. There is a separate category of proposed explanation that occasionally surfaces in popular discussions of the void, involving the idea that it might represent evidence of a collision between our universe and another universe entirely, sometimes framed within speculative multiverse cosmology, or alternatively, that its emptiness might be explained by the activity of an extremely advanced civilization, capable of manipulating matter and energy on a galactic scale, a concept sometimes associated with the theoretical Kardashev scale used to categorize hypothetical civilizations by their energy consumption. It is important to be direct about where these ideas stand scientifically. Neither has any observational evidence supporting it. The multiverse collision idea originates from certain theoretical frameworks in cosmology, including some versions of eternal inflation, that do predict the mathematical possibility of other regions of spacetime existing beyond our observable universe. And in some of these models, bubble collisions between separate inflating regions are theoretically possible. However, these models do not currently make any specific, testable prediction that would connect such a collision to the particular size, shape, or location of a void like Boötes, and no signature consistent with a bubble collision, which cosmologists have actually searched for in subtle patterns within the cosmic microwave background, has ever been confirmed anywhere in the sky. The advanced civilization explanation fares even worse under scrutiny. There is no known physical mechanism by which any civilization, however technologically advanced, could plausibly clear galaxies out of a region 300 million light-years across, a scale so vast that light itself takes hundreds of millions of years just to cross it, meaning any coordinated engineering project on that scale would require timescales and energy requirements that dwarf anything physically conceivable within our current understanding of energy, matter, and the speed of light as an ultimate cosmic speed limit, Both of these ideas belong firmly in the category of speculation rather than science. Interesting as thought experiments about the outer edges of what physics might theoretically allow, but entirely unsupported by any current evidence, and not treated as serious competing explanations within the professional astrophysics community studying the void. What remains, once the more speculative ideas are set aside, is a genuinely fascinating and still partially unresolved scientific question, just a more modest one than headlines sometimes suggest. Is the Boötes void purely the product of ordinary gravitational structure formation, acting on the same statistical fluctuations that produced every other void in the observable universe, just realized in an unusually extreme form? Or does its existence hint that our models of the early universe, whether involving inflation, dark matter, or some other ingredient not yet fully understood, need refinement to correctly predict how often objects this extreme should occur? Neither answer represents a crisis for physics in the sense of overturning established theory. Both answers represent normal, productive science, the kind that proceeds by testing models against their most extreme and uncomfortable examples, refining them where they fall short, and building greater confidence in them where they hold up. This is really the heart of what makes the Boötes void valuable to cosmology, independent of any dramatic narrative. Extreme structures function as stress tests. A model of the universe that only works for typical average regions is a weaker model than one that correctly predicts, or at least comfortably accommodates, the rare and unusual corners of the cosmos as well. Every time astronomers map another void this large, whether in Boötes or in newly discovered supervoids found through deeper and wider modern surveys, they add another data point to an ongoing statistical test of the entire framework of modern cosmology. So far, that framework has held up, but the test is not finished, and every new instrument capable of mapping galaxies across greater distances and fainter magnitudes adds another opportunity to either strengthen that confidence further or uncover the first real crack that would force cosmologists to rethink part of the story. To understand just how significant the Boötes void is, it helps to place it alongside the other great voids that astronomers have mapped since Kirshner's original 1981 survey. The universe, it turns out, is full of large underdense regions, though very few come close to matching Boötes in scale. Our own cosmic neighborhood sits near the edge of a structure called the local void, a considerably smaller but still substantial underdense region, roughly 150 million light-years across. Close enough that its gravitational influence has been measured through its subtle effect on the motion of nearby galaxies, including a gentle gravitational push that contributes to the Milky Way's own motion through space. Farther afield, deep sky surveys have identified structures like the giant void in the constellation Canes Venatici, spanning well over 300 million light-years, placing it in the same size class as Boötes itself, and helping demonstrate that while such enormous voids are rare, the Boötes void is not entirely unique. One of the more intriguing connections in recent cosmology involves a link between large supervoids and a peculiar cold spot found in the cosmic microwave background, the faint relic radiation left over from roughly 380,000 years after the Big Bang, when the universe first became transparent to light. This cosmic microwave background is remarkably uniform, but not perfectly so, and one particular region of the sky, sometimes called the cold spot, shows a temperature slightly lower than its surroundings, a discrepancy that some researchers have proposed could be explained by an enormous supervoid lying along that line of sight, in the direction of the constellation Eridanus. The physical mechanism proposed to explain this connection is called the integrated Sachs-Wolf effect, in which light from the cosmic microwave background passing through a large void loses a small amount of energy overall, because the gravitational boost it receives falling into the void's edge is not fully compensated by an equal gravitational pull climbing back out, an imbalance that only occurs because the universe's expansion is accelerating due to dark energy. In a universe without dark energy, the energy gained falling in and the energy lost climbing out would cancel exactly. With dark energy stretching space in the meantime, they do not, leaving a faint but measurable cooling imprinted on the light that passes through. This proposed explanation for the cold spot remains genuinely debated within the cosmology community, with some studies supporting the connection to a supervoid and others finding the statistical evidence too weak to confirm it with confidence, or arguing that the known Eridanus supervoid is not large enough or deep enough on its own to fully account for the observed cooling. The Boötes void itself has not been directly implicated in this particular puzzle, since it lies in a different direction of the sky, but the broader technique, using supervoids to search for subtle imprints on the cosmic microwave background, represents one of the more promising indirect tools available for studying the relationship between large-scale cosmic structure and the influence of dark energy. If voids the size of Boötes leave a measurable, predictable imprint on the ancient light passing through them, cataloguing more of these giant underdense regions across the sky becomes a genuinely useful strategy for testing our understanding of dark energy independent of other methods, such as measuring the brightness of distant supernovae or tracking the subtle rhythmic pattern, known as baryon-acoustic oscillations, imprinted in the large-scale distribution of galaxies. This dark energy connection brings the story of the Boötes void into contact with one of the deepest open questions in all of modern physics. Dark energy makes up roughly 2/3 of the total energy density of the universe, and it is responsible for the accelerating expansion first confirmed through supernova observations in the late 1990s, work that was later recognized with the 2011 Nobel Prize in Physics. Despite its dominant role in shaping the universe's fate, dark energy remains almost entirely mysterious. Physicists do not know whether it behaves as a true cosmological constant, a fixed property of empty space itself as originally proposed by Einstein, or whether it changes subtly over cosmic time, a possibility that would point toward new physics beyond the current standard model. Because voids grow larger and emptier over time specifically as a result of the interplay between gravity and cosmic expansion, their sizes and growth rates carry an imprint of the expansion history of the universe, and by extension, an imprint of dark energy's behavior throughout cosmic time. A void as extreme as Boötes, tracked carefully over years of repeated observation, offers cosmologists another thread of evidence to pull on in the ongoing effort to understand what dark energy actually is, and whether it will continue accelerating the expansion of the universe indefinitely, or whether its influence might change as the universe continues to age. The discovery of the Boötes void did not happen in isolation. It arrived at a pivotal moment in the history of observational cosmology, right as astronomers were beginning to shift from studying galaxies as isolated objects to mapping their positions across 3 dimensions on an unprecedented scale. Before large redshift surveys became possible, astronomers could observe a galaxy's brightness, its shape, and its spectrum, but building an actual 3-dimensional map of how galaxies were distributed through space required measuring redshifts for thousands of galaxies one at a time, a painstaking process that only became practical with improvements in spectroscopic instrumentation through the 1970s and 80s. The original survey that found the Boötes void was part of this broader wave of discovery, and the void's existence became one of the earliest and most dramatic pieces of evidence that the universe's large-scale structure was not smooth, but woven through with both dense filaments and enormous underdense gaps. Just a few years after the Boötes void discovery, in 1989, astronomers Margaret Geller and John Huchera used a similarly styled redshift survey to identify what became known as the Great Wall, later renamed the CFA Great Wall in reference to the Center for Astrophysics survey that found it, an enormous filament of galaxies stretching over 500 million light-years. At the time, the largest coherent structure ever mapped in the universe, the discovery of both an enormous void and an enormous filament within less than a decade of one another helped cement the modern picture of the cosmic web in the minds of astronomers, structure and emptiness existing side by side, each one the necessary consequence of the other, since matter pulled out of a void has to accumulate somewhere, and that somewhere tends to be the walls and filaments bordering it. These early discoveries were made using what would today be considered remarkably modest technology, surveying a few thousand galaxies at a time using instruments that, by modern standards, moved slowly and covered only small patches of sky. Since then, the scale of galaxy surveys has grown by staggering orders of magnitude. The Sloan Digital Sky Survey, which began operations in 2000 and has continued through multiple phases and instrument upgrades over the decades since, has measured redshifts for millions of galaxies and quasars, producing 3-dimensional maps of the universe, covering a substantial fraction of the observable sky. Within this vastly larger dataset, astronomers identified an even more enormous structure than the original CFA Great Wall, informally called the Sloan Great Wall, stretching over 1.3 billion light-years, and confirmed the presence of many additional large voids across the mapped volume. helping to place the Boötes void within a broader statistical population of similarly extreme structures rather than treating it as a singular anomaly. Modern survey instruments continue to push this frontier further. The Dark Energy Spectroscopic Instrument, a specialized telescope system designed specifically to measure the redshifts of tens of millions of galaxies and quasars with extraordinary efficiency, has been mapping the large-scale structure of the universe with a level of precision and volume that dwarfs anything available to the astronomers who first found the Boötes void. Its primary scientific goal is to measure the expansion history of the universe with enough precision to constrain the properties of dark energy directly, using the statistical pattern of galaxy clustering, including the frequency, size, and distribution of voids. As one of several complementary tools, early results from this survey, released across the middle of the 2020s, have already provided some of the most precise measurements yet of the universe's expansion rate at different points in cosmic history, and continued analysis of its enormous void catalogue is expected to refine our understanding of exactly how common and how extreme structures like the Boötes void are allowed to be under the standard cosmological model. Looking further ahead, an entire generation of new observatories is poised to transform void research even further. The Vera Rubin Observatory, situated in Chile and designed to repeatedly photograph the entire visible southern sky over a period of roughly 10 years, will generate an unprecedented volume of data on galaxy positions, brightness, and structure, enabling far more sensitive void detection across a much larger cosmic volume than any previous survey. The Nancy Grace Roman Space Telescope, expected to begin science operations later this decade, will complement ground-based efforts with a wide-field infrared view capable of detecting fainter, more distant galaxies than most current instruments, directly addressing the observational bias concern discussed earlier. The possibility that some voids appear emptier than they truly are, simply because existing telescopes cannot detect their faintest inhabitants. The European Space Agency's Euclid mission, already collecting data as of the mid-2020s, is specifically designed to map the geometry of the universe's expansion and the growth of large-scale structure with high precision, providing yet another independent dataset against which the statistics of extreme voids like Boötes can be tested. Taken together, this new generation of instruments represents the most promising path toward finally resolving the deeper questions the Boötes void first raised more than 4 decades ago. Is its extreme size a natural, if rare, consequence of standard structure formation, fully consistent with the cosmological principle once enough of the universe has been surveyed to properly understand the statistics involved? Or does it, alongside any similarly extreme voids these new surveys might uncover, represent the leading edge of evidence that some part of the standard cosmological model needs adjustment, whether in the properties of dark matter, the details of cosmic inflation, or the behavior of dark energy across cosmic time? The honest answer, as of now, is that the case remains open, genuinely open, in the sense that reasonable, well-informed scientists continue to disagree about how much weight to place on outliers like Boötes, and continue to design new observational campaigns specifically to settle the question with better data rather than by argument alone. Some of the most detailed insight into what life inside a void actually looks like has come from a dedicated research effort known informally as the Void Galaxy Survey, a project that selected galaxies specifically because they sit deep within the interiors of large voids, identified through earlier redshift mapping, rather than being found incidentally the way most void galaxies had been studied before. Researchers involved in this and similar projects combined observations from optical telescopes with radio observations sensitive to neutral hydrogen gas, the raw fuel from which new stars are born, using large radio survey programs capable of detecting the faint radio emission produced by hydrogen atoms even in galaxies too faint or too diffuse to study easily through visible light alone. This combination of techniques confirmed what earlier, smaller studies had suggested. Void galaxies tend to carry unusually large reservoirs of neutral hydrogen relative to their stellar mass, consistent with a picture in which these galaxies have converted a smaller fraction of their available gas into stars over cosmic history, precisely because their isolation has spared them the gas-stripping and merger-driven starburst events that accelerate gas consumption in denser environments. This same body of research has also probed the shapes and orientations of void galaxies, testing an intriguing theoretical prediction. Because voids are underdense but not perfectly empty, And because the sparse matter within them still traces out faint filamentary structure, models of structure formation predict that galaxies within voids should preferentially align their rotation axes with the local filaments and sheets of matter surrounding them, a subtle geometric echo of the larger cosmic web pattern that shaped their formation. Detecting this alignment observationally is difficult, since it requires precise measurements of galaxy orientation across a large enough sample to overcome the considerable natural scatter introduced by each galaxy's individual formation history. But several studies focused on void galaxies, including some using data relevant to structures like the Boötes void, have reported statistically significant alignment signals consistent with these theoretical predictions. Results like this matter a great deal because they represent an independent, largely unrelated line of evidence supporting the standard picture of how cosmic structure grows from gravitational collapse acting on the early universe's density fluctuations, adding further weight to the conclusion that a void's extreme emptiness, however striking, remains a natural outcome of ordinary physics operating at an unusual scale, rather than a signal of something fundamentally amiss. Gravitational lensing has provided another valuable, largely independent probe of what lies within voids, including large ones comparable to Boötes. When light from a distant background galaxy or quasar passes near a foreground mass concentration, its path bends very slightly, an effect predicted by general relativity and confirmed observationally many times over since Arthur Eddington's famous 1919 solar eclipse expedition first tested Einstein's theory directly. The same principle works in reverse for underdense regions. Light passing through a void, where the surrounding mass is less than the cosmic average, bends very slightly less than it would traveling through an average patch of space, producing an extremely subtle, statistically detectable weak lensing signature. By carefully measuring the tiny coherent distortions in the shapes of background galaxies seen through and around large voids, researchers can build an independent estimate of just how underdense these regions truly are in total mass, including the invisible dark matter that dominates the universe's mass budget, but produces no light of its own. Weak lensing studies of voids broadly consistent in scale with Boötes have generally supported the picture drawn from galaxy counts alone, finding total mass deficits in line with what standard cosmological models predict for regions of comparable size, offering yet another consistency check that continues to support, rather than undermine, the basic framework connecting the Boötes void to ordinary, well-understood physics. None of this diminishes how genuinely strange and wonderful the void remains as an object of study. It simply relocates the wonder from the realm of broken physics into the realm of physics operating at its most extreme and least intuitive. There is something quietly profound in the idea that the same handful of physical laws, gravity pulling matter together, the residual imprint of quantum fluctuations from the earliest fraction of a second after the Big Bang, and the slow, patient unfolding of cosmic time, can produce both the crowded, star-filled splendor of a galaxy cluster and the vast, near-silent darkness of a supervoid 300 million light-years across, using nothing more exotic than the ordinary rules already written into the standard model of cosmology. Researchers continue to explore whether the sparse filament of galaxies threading through the Boötes void connects, even more faintly, to similar structures bridging neighboring underdense regions elsewhere in that part of the sky. Part of a broader effort to map what some cosmologists have started calling the void network, an interconnected system of underdense channels running between the denser walls and filaments of the wider cosmic web. Mapping this network in detail requires exactly the kind of large volume, high-sensitivity survey data that instruments like the Dark Energy Spectroscopic Instrument, the Vera-Rubin Observatory, and the Euclid mission are only now beginning to provide in sufficient quantity. If these deeper corridors of near emptiness turn out to connect major voids across hundreds of millions or even billions of light-years, it would refine our understanding of how the cosmic web's least dense regions are organized, complementing the already well-established picture of how its densest regions, the great filaments and superclusters, are connected to one another. There is also a longer, stranger story hidden in the relationship between voids and the ultimate fate of the universe. One that reframes the Boötes void not just as a curiosity of the present cosmic era, but as a preview of where the entire universe is gradually heading. Because dark energy drives an accelerating expansion, and because that acceleration works to stretch underdense regions, even emptier over time while pulling matter more tightly into the densest structures nearby, Cosmologists studying the far future of the universe have concluded that voids are destined to grow, not just in this particular pocket of sky, but as a general feature of cosmic evolution. Trillions of years from now, long after the last stars have exhausted their nuclear fuel, the observable portion of the universe accessible to any future observer will have shrunk dramatically, not because the universe itself is shrinking, but because accelerating expansion will have carried an ever-increasing majority of galaxies beyond the cosmic horizon, the boundary past, which light can no longer reach us even after traveling for the entire remaining lifespan of the universe. In some very real sense, most of the galaxies currently visible to us are already fated to eventually disappear from view, dropping below this horizon into a kind of permanent cosmic isolation, while whatever companions remain gravitationally bound to our own local group, primarily the Milky Way and Andromeda, drift alone within an ever-expanding void of their own making. Framed this way, a structure like the Boötes void is not simply an unusual feature of the present-day universe. It is, in a sense, a glimpse forward in time, an early and unusually dramatic example of the same emptying process that will eventually claim the entire observable cosmos as dark energy continues to stretch space apart, faster than gravity can hold structure together. Across ever larger distances, understanding exactly how voids like Boötes formed, how quickly they grow, and how their internal structure evolves over billions of years, therefore offers more than a solution to one strange regional puzzle. It offers a working model, tested against real data collected today, for a process that will eventually reshape the entire visible universe, transforming what is now a richly interconnected web of galaxies into something closer to a collection of isolated island universes, each one gradually losing sight of all the others. None of this is meant to induce a sense of dread. It unfolds across timescales so vast, trillions of years rather than millions, that they exist almost entirely outside any time frame relevant to human experience, or even to the remaining lifespan of the Sun and Earth, which will themselves undergo their own transformations long before dark energy's slow work on the largest scales becomes noticeable to anyone living through it. Rather, it offers a kind of long-view perspective, a reminder that studying an object like the Boötes void connects directly to some of the deepest and most consequential open questions in physics. Questions about the ultimate nature of dark energy, the long-term fate of cosmic structure, and the eventual observational isolation that awaits every civilization anywhere in the universe, patient enough to keep watching the sky for long enough. After more than 4 decades of study, the Boötes void has not resolved into a simple story with a clean, satisfying ending, and that is entirely appropriate for an object this genuinely strange. What began as an apparent anomaly in an early 1981 redshift survey has evolved into one of the most productive natural laboratories available to modern cosmology, a single region of sky that has helped refine our understanding of galaxy evolution, sharpened statistical tests of the standard cosmological model, provided an independent probe of dark matter distribution through gravitational lensing, and offered a preview, however distant in time, of the emptying process that will eventually reshape the entire observable universe. What remains unresolved is not whether the void exists, or roughly how large it is, or even whether it is broadly compatible with standard cosmology, since on all of these points the evidence, while not perfectly settled in every detail, points in a fairly consistent direction. What remains genuinely open is the finer-grained question of exactly how common structures this extreme should be. How much of the void's apparent emptiness reflects true underdensity versus the practical limits of past surveys, and whether the growing catalogue of similarly enormous voids being uncovered by next-generation instruments will continue to comfortably fit within the standard model's predictions, or begin to strain them in ways that finally force a meaningful revision to some part of the theory. Answering that question will likely take another decade or more of dedicated observation, drawing on exactly the kind of large-scale, high-precision survey work already underway across observatories. On the ground and in space, there is something fitting about the fact that one of the emptiest places astronomers have ever mapped has turned out to be so scientifically full of implications for dark matter, dark energy, galaxy evolution, and the eventual fate of the cosmos itself. The 300 million light-year gap in the constellation Boötes is not a wound in the fabric of physics, and it never required breaking any law of nature to exist. It required only patience, gravity, and roughly 14 billion years of quiet cosmic time. The same patient forces that built every galaxy, every star, and every atom heavy enough to eventually form a planet, a person, and the curiosity capable of noticing, from a small blue world tucked along an ordinary filament of the cosmic web, that somewhere out past the herdsman, the universe had left an unusually large space unfilled, and had left it there specifically for someone, someday, to wonder why. Long before Robert Kirshner's survey stumbled onto the void that would eventually carry Boötes' name, theoretical cosmologists had already begun predicting that the universe's large-scale structure should look something like a sponge, riddled with both dense filaments and enormous empty cavities, rather than a smooth, evenly distributed sea of galaxies. In the early 1970s, the Soviet astrophysicist Yakov Zeldovich developed a mathematical framework, now often called the Zeldovich approximation, describing how small initial density fluctuations in the early universe would evolve under gravity into flattened, sheet-like structures nicknamed pancakes, which would later intersect to form filaments and eventually nodes, leaving large gaps in between where matter had been evacuated rather than accumulated. Around the same period, the Estonian astronomer Janne Nasto and his collaborators were independently analyzing the distribution of galaxies and superclusters and arriving at strikingly similar conclusions, proposing what they described as a cellular structure to the universe, dense cell walls surrounding vast, comparatively empty interiors. When redshift surveys throughout the late 1970s and early 1980s finally accumulated enough three-dimensional data to test these theoretical predictions directly, the discovery of enormous voids, including the one in Boötes, served as remarkably direct observational confirmation of ideas that theorists had reasoned their way toward years earlier using little more than the physics of gravitational instability and pen and paper calculations. This is one of the more satisfying stories in the history of cosmology, an instance where theory and observation arrived at the same striking picture of the universe from two completely different directions, lending each other mutual support almost immediately upon first contact. Identifying a void precisely and measuring its size in a way that different research groups can compare consistently turns out to be a more subtle technical challenge than it might first appear. Unlike a galaxy or a star, a void has no sharp physical boundary, no clearly defined edge where emptiness suddenly gives way to normal density. Instead, astronomers rely on a variety of mathematical algorithms designed to identify underdense regions within a three-dimensional map of galaxy positions, each with its own strengths and limitations. Some of the earliest and simplest techniques search for the largest possible sphere that could be drawn within a survey volume while containing no galaxies above a certain minimum density threshold, an approach that is intuitive and easy to compute, but sensitive to exactly where the sphere happens to be centered and how the density threshold is defined. More sophisticated modern techniques, including an approach borrowed from image processing called the watershed algorithm, treat the three-dimensional density field of the universe almost like a topographic map, identifying voids as the low-lying basins that would naturally fill first if you imagined pouring water into the cosmic landscape, allowing for voids of irregular, non-spherical shapes that more accurately reflect how these structures actually look once you account for their complex, filament-threaded interiors and their often lumpy, asymmetric boundaries. This technical detail matters a great deal for understanding exactly what number to attach to the Boötes void size. Depending on which void-finding algorithm is used, which density threshold is applied, and which underlying galaxy survey provides the input data, published estimates for the void's diameter have ranged from as small as roughly 250 million light-years up toward the frequently cited figure of 330 million light-years. This is not a sign of sloppy science or genuine disagreement about the void's basic nature. It reflects the reality that voids, unlike planets or stars, do not have crisp, universally agreed upon boundaries, and any single number used to describe their size necessarily depends on the specific, clearly documented methodology used to measure it. Modern papers studying the Boötes void, and large voids more generally, are typically careful to specify exactly which technique and threshold produce their reported figures, precisely so that later researchers can make fair, apples-to-apples comparisons across different studies rather than being misled by superficially different numbers that actually describe very similar underlying structures. This methodological complexity connects to a broader and genuinely unresolved puzzle in the study of cosmic voids, one that astrophysicists sometimes refer to informally as the void phenomenon, a name popularized through the work of the cosmologist James Peebles in the early 2000s. The puzzle runs roughly as follows: standard cold dark matter simulations, which successfully reproduce the large-scale filament and void structure of the observable universe with impressive accuracy overall, also predict that voids should contain a substantial population of small, faint dwarf galaxies, formed within relatively low-mass clumps of dark matter that are expected to exist even within underdense regions. Observationally, however, voids consistently appear to contain noticeably fewer of these small galaxies than simulations predict, a discrepancy that has persisted in various forms across multiple generations of both simulations and observational surveys. Several possible resolutions have been proposed. It is possible that many of the predicted dwarf galaxies do exist within voids, including the Boötes void, but remain too faint for current telescopes to detect efficiently, echoing the same observational bias concerns discussed earlier regarding the void's overall galaxy count. It is also possible that some physical process specific to low-density environments, perhaps related to how efficiently gas can cool and collapse into stars within such sparse surroundings, genuinely suppresses dwarf galaxy formation within voids compared to what basic dark matter clumping alone would predict. A third possibility, explored primarily through more detailed simulations, is that the standard properties assumed for dark matter, including how it clusters on the smallest scales, may need some refinement to correctly match what voids actually look like once observed in sufficient detail. This remains one of the more actively debated open questions connecting void research directly back to fundamental, unresolved questions about the nature of dark matter itself and structures like the Boötes void, precisely because of their extreme size and relative proximity, continue to serve as important test cases for resolving it. The Boötes void itself has been revisited by astronomers many times since its initial discovery, each new generation of instruments adding finer detail to the picture first sketched out in 1981. Follow-up redshift surveys conducted through the 1980s and 90s, including work led by researchers such as Fiona Kopylova and Alexander Kopylov, refined the original galaxy count within the void's boundaries and helped confirm that the loose filament of galaxies running through its interior was a genuine structural feature rather than a statistical artifact of small sample sizes. Later studies using the Hubble Space Telescope examined individual galaxies within the void at higher resolution than ground-based instruments could achieve, allowing astronomers to study their internal structure, star formation patterns, and morphology in far greater detail. These observations consistently reinforce the broader picture developed through wider void galaxy surveys, showing star-forming disk galaxies with elevated gas fractions and comparatively undisturbed structure, exactly the signature expected from a population that has spent most of cosmic history evolving in near-total isolation from the kind of gravitational encounters that reshape galaxies in busier environments. Some of the more recent observational work on the Boötes void has focused specifically on trying to resolve the observational bias question raised earlier, using deeper imaging surveys capable of detecting fainter galaxies than the instruments available in the 1980s and 90s. These deeper searches have indeed turned up additional void member galaxies beyond the roughly 60 originally catalogued, though the overall picture of the void as dramatically underdense compared to the cosmic average has held up consistently across every round of improved observation. This pattern, modest upward revisions in galaxy count paired with a stable, robust conclusion about overall underdensity, is exactly what a careful, self-correcting scientific process should produce, and it stands as a useful case study in how observational astronomy refines its picture of a phenomenon over decades, without needing to overturn the basic conclusion reached by the earliest pioneering studies. Voids like Boötes have also become an increasingly important tool for testing an entirely different category of theoretical idea, one that goes beyond simply refining the standard cosmological model and instead asks whether gravity itself might behave slightly differently than general relativity predicts on the very largest cosmic scales. A family of theories broadly described as modified, gravity proposes that some or all of the effects currently attributed to dark energy and dark matter might instead arise from subtle deviations in how gravity operates across enormous distances. deviations too small to detect within the solar system or even within a single galaxy, but potentially significant when averaged across structures spanning hundreds of millions of light years. Because voids represent some of the most extreme, lowest density environments available anywhere in the observable universe, they offer a particularly sensitive testing ground for these ideas. Many modified gravity theories predict that their deviations from standard general relativity should become most noticeable precisely in low-density regions, since the effects some of these theories propose are often designed to remain hidden or screened in denser environments through various theoretical screening mechanisms, while becoming unmasked within the emptiness of a void's interior. Researchers have used detailed measurements of galaxy motions and weak lensing signals within large voids to place some of the tightest available constraints on several popular modified gravity models, and so far, these tests have continued to favor standard general relativity, combined with conventional dark energy, over most of the proposed alternatives, though the field remains active, and voids continue to serve as one of the most promising remaining laboratories for testing gravity's behavior at the largest scales nature has to offer. There is a broader lesson embedded in all of this cross-disciplinary interest in a single patch of empty sky, one that extends well past the specific details of dark matter, dark energy, or modified gravity. The Boötes void has become, almost by accident, a kind of meeting point for several of the biggest open questions in modern physics, each approaching the same underdense region of space from a different angle and asking a slightly different version of the same underlying question. Does the universe behave the way our best current models say it should, all the way out to the most extreme examples nature happens to provide? Or are there subtle discrepancies hiding in the details? Discrepancies that might eventually point the way toward the next major revision of physical theory. Very few individual astronomical objects manage to sit at the intersection of quite so many active research programs simultaneously, and that alone is a reasonable measure of just how scientifically valuable this particular gap in the sky has turned out to be. Much of what astronomers know about how a structure like the Boötes void actually forms comes not from telescopes alone, but from an entirely different kind of scientific instrument, the supercomputer. Because the formation of cosmic voids unfolds over billions of years, far longer than any human research career, let alone any single observational campaign, cosmologists rely heavily on large-scale computer simulations to model the process directly, starting from initial conditions closely matched to the density fluctuations measured in the cosmic microwave background, and then evolving those conditions forward through simulated cosmic time, using the known physics of gravity, dark matter, and the expansion of space. One of the most influential efforts of this kind, known as the Millennium Simulation, tracked the gravitational evolution of more than 10 billion simulated particles of matter across a cube of simulated space over 2 billion light-years on a side, reproducing a startlingly realistic version of the cosmic web, complete with filaments, clusters, and voids in broadly the same proportions and general appearance as observed in real galaxy surveys. Later simulation projects have pushed this approach even further, incorporating not just the gravitational physics of dark matter, but also the much more complex physics of ordinary gas, star formation, and the feedback processes by which forming stars and growing black holes can heat and redistribute the gas around them, producing simulated universes detailed enough to predict not just where galaxies should form, but roughly what they should look like, how bright they should be, and how their properties should depend on their surrounding environment, including whether that environment happens to be a dense cluster or the sparse interior of a void comparable to the one in Boötes. These simulations serve a purpose that observation alone cannot fully replace. A single observed void, however well studied, is only one example drawn from what is presumably a much larger population of similar structures scattered throughout the universe, most of them far too distant or too faint for current telescopes to study in comparable detail. A well-calibrated simulation, by contrast, can generate thousands of statistically independent voids within a single simulated volume, allowing researchers to build a genuine statistical distribution of void sizes, shapes, and internal galaxy populations, and then ask precisely where an unusual real-world example like the Boötes void falls within that distribution. This is how cosmologists arrived at the earlier conclusion that the void represents a rare but not impossible outlier rather than a genuine violation of the standard model. That conclusion did not come from intuition or from comparing Boötes informally to a small handful of other known voids. It came from generating large simulated populations of voids under the assumptions of standard cosmology and directly checking what fraction of them come anywhere close to matching the size and emptiness observed in the real structure sitting out past the constellation of the herdsman. Simulations of this kind have also proven valuable for a more subtle purpose, testing exactly how sensitive void statistics are to small changes in the underlying assumptions that go into a cosmological model. By rerunning essentially the same simulation multiple times, each time adjusting a single parameter, such as the total amount of dark matter, the precise statistical properties of the initial density fluctuations, or the specific behavior assumed for dark energy, researchers can map out how the predicted population of extreme voids shifts in response. This kind of systematic parameter exploration is exactly how cosmologists identify which aspects of void statistics carry the most diagnostic power for distinguishing between competing theoretical models, and it has helped establish supervoid statistics, including analysis of structures directly comparable to Boötes, as one of several complementary tools cosmologists now use, alongside more traditional techniques like measuring the cosmic microwave background or tracking the brightness of distant supernova, each approach offering a partially independent check on the same underlying cosmological framework. The interplay between observation and simulation, captured in this research, also illustrates something valuable about how modern science actually progresses on genuinely difficult, large-scale questions. Neither telescopes nor supercomputers alone could have produced today's fairly sophisticated understanding of what the Boötes void represents and what it does not. It required both, working in a continuous back and forth. Observations motivating new simulations designed to test whether a given structure is plausible under known physics, and simulations in turn motivating new observational campaigns designed to check predictions that would otherwise remain purely theoretical, such as the expected population of faint dwarf galaxies within voids, or the subtle alignment of void galaxy rotation axes with the surrounding faint filamentary structure. This back and forth has been running continuously since the early 1980s and shows no sign of concluding anytime soon, which is, in its own way, exactly what a healthy and still productive area of scientific research is supposed to look like. There is also a quieter, more human dimension to this decades-long research effort, one that rarely makes it into technical papers but shapes how the science actually gets done. Modern void research, and large-scale structure cosmology more broadly, has become a deeply collaborative, international undertaking, involving research teams spread across dozens of countries, sharing enormous public datasets that would have been unimaginable to the small team that first noticed the emptiness in Boötes back in 1981. Major surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument release their catalogues publicly, allowing researchers anywhere in the world, often working with limited resources compared to the largest, most well-funded observatories, to conduct original analysis using exactly the same underlying data as scientists at major research institutions. This openness has meaningfully accelerated the pace of discovery, allowing independent groups to cross-check one another's void catalogues, statistical methods, and conclusions using shared, transparent datasets rather than working in isolation with proprietary information. This same spirit of openness has occasionally extended beyond professional astronomers entirely. Citizen science projects, in which members of the public volunteer to help classify astronomical images through carefully designed online platforms, have made real contributions to galaxy research broadly, including work relevant to understanding galaxy morphology within different cosmic environments. Projects of this kind have successfully identified rare or unusual galaxies that automated computer algorithms initially missed, precisely because human pattern recognition remains, for certain kinds of visual classification tasks, surprisingly difficult for software to fully replicate. While no citizen science project has focused specifically and exclusively on the Boötes void, the broader galaxy classification datasets these projects have produced feed into the same large public catalogues that void researchers draw on, meaning that in a genuinely indirect but real sense, the ongoing effort to understand structures like the Boötes void has benefited from the participation of thousands of interested members of the public, working alongside professional astronomers, rather than merely reading about their conclusions after the fact. It is worth asking, too, what any of this would actually look like from the inside, not as an exercise in idle imagination, but because thinking through the practical experience of a void helps clarify just how different the phrase empty space truly is from the science fiction image of a featureless, starless gulf. An observer situated somewhere near the center of the Boötes void, on a hypothetical planet orbiting one of its sparse resident galaxies, would not experience anything close to total darkness. Their own galaxy would still fill a portion of their sky with the same dense scattering of stars, star clusters and interstellar gas found in any galaxy anywhere in the universe, since a void's emptiness describes the space between galaxies, not the space within them. What would be genuinely different is the view beyond their home galaxy, where an observer on Earth can see thousands of other galaxies with a sufficiently powerful telescope, all relatively close by on a cosmic scale. Our hypothetical void observer would find their nearest galactic neighbors tens of millions of light years distant, roughly the kind of separation that exists between our own Milky Way and galaxies well beyond the boundary of the local group. Their night sky, in other words, would look like a normal galaxy's night sky in almost every respect, except that the broader extragalactic landscape beyond their own galactic disk would appear remarkably, unusually sparse, populated by faint, widely scattered points of light, rather than the rich tapestry of nearby galactic neighbors that fills deep exposures of our own patch of sky. This detail matters because it helps dismantle a common misconception built into some of the more dramatic popular framing of the void. The idea that finding yourself inside it would mean confronting some kind of existential darkness. In practice, it would mean something closer to profound isolation on the largest scales, a night sky nearly empty of other galaxies paired with an entirely ordinary, star-filled night sky on the more local scale of one's own galactic home. That distinction between local abundance and large-scale isolation connects to a genuinely important question in the study of planetary habitability and, by extension, astrobiology, the scientific study of the potential for life beyond Earth. A planet orbiting a star within a void galaxy would experience the same basic physics of stellar formation, chemical enrichment through supernova explosions, and planetary formation as any other planet anywhere else in the universe, since the void's underdensity concerns the spacing between galaxies rather than the internal physics of star and planet formation within a given galaxy. The most meaningful difference likely to affect any hypothetical life within a void concerns the pace of galaxy evolution itself. Because void galaxies experience so few of the mergers, interactions and starbursts common in denser environments, their chemical enrichment history, the gradual buildup of heavier elements produced by successive generations of stars and released into the surrounding gas through supernova explosions, would likely proceed more slowly and steadily than in a busier galactic environment. Since heavier element enrichment is often accelerated by the intense, merger-triggered starburst episodes common in interacting galaxies, this is a genuinely open area of research, and no observational evidence currently suggests any meaningful difference in the likelihood of life arising within void galaxies compared to galaxies anywhere else. But it stands as one more example of how studying an extreme environment like the Boötes void connects, sometimes in unexpected ways, to much broader questions about the conditions required for life to emerge and persist across cosmic history. Although the James Webb Space Telescope has not been used to directly image the sparse galaxy population within the Boötes void itself, since its instruments are optimized for detecting extremely faint, distant, and often highly redshifted light, rather than surveying relatively nearby galaxies across a wide area of sky. Its broader scientific contributions have proven relevant to void research in a less direct but still meaningful way. One of the telescope's central missions has been observing galaxies from the earliest few hundred million years after the Big Bang, an epoch sometimes called cosmic dawn, when the very first generations of stars and galaxies were assembling out of primordial gas. Because the same initial density fluctuations that seeded the first galaxies also seeded the eventual voids and filaments of the mature cosmic web, improved observational constraints on how quickly and how vigorously galaxy formation proceeded during this earliest era feed, directly into the same theoretical models used to predict how large a void could plausibly grow by the present day. Several of the telescope's early findings, including the discovery of galaxies that appear more massive and more fully formed at earlier cosmic times than many pre-launch models had predicted, have prompted cosmologists to revisit certain assumptions about the efficiency of early galaxy formation and star formation more broadly. While this line of research bears more directly on questions of early galaxy assembly than on the Boötes void specifically, it illustrates the same underlying principle that runs through the entire modern study of large-scale structure, that observations at one end of cosmic history, whether the earliest galaxies ever formed or the largest voids ever carved out, ultimately feed into a single, unified theoretical framework. And unexpected results in one corner of that framework tend to ripple outward, prompting re-examination of assumptions used everywhere else within it, including the statistical models cosmologists rely on to judge whether an object like the Boötes void counts as a comfortable, if rare, prediction of standard cosmology, or as a genuine outlier demanding closer scrutiny. The scale of modern void research has also grown considerably beyond anything imaginable to the small team that first identified the Boötes void using a survey of only a few thousand galaxies. Contemporary catalogues built from the Dark Energy Spectroscopic Instrument and its predecessor surveys now contain many thousands of individually identified voids spanning a huge range of sizes, from relatively modest underdense pockets, tens of millions of light-years across, up to rare supervoids approaching, and in a small number of documented cases exceeding the scale of Boötes itself. This much larger sample size has transformed void research from the study of a small number of individually remarkable objects into a genuinely robust statistical science, allowing researchers to measure not just whether extreme voids exist, but precisely how their sizes, shapes, and internal galaxy populations are distributed across the full range the universe has to offer, and to track subtle trends in that distribution across different cosmic epochs. Since more distant, and therefore more ancient, voids reveal what void statistics looked like earlier in the history of the universe, before billions of additional years of gravitational evolution had a chance to further empty them out. Comparing the statistical properties of nearby, well-evolved voids like Boötes against the properties of younger, more distant voids observed at earlier cosmic epochs offers cosmologists a genuinely powerful, time-resolved test of structure formation theory, one that simply did not exist in any meaningful form during the decades immediately following the Boötes void's initial discovery, and one that continues to grow more precise and more statistically powerful with every new survey data release. Even with all of this accumulated observational and theoretical progress, a handful of specific, well-defined questions about the Boötes void remain genuinely unresolved, and it is worth being precise about what they are, rather than leaving the impression that everything meaningful about the void has already been settled. The first concerns the void's true three-dimensional shape. Early analyses generally treated the void as roughly spherical for simplicity, since that assumption makes many calculations considerably more tractable. But more recent work using improved void-finding algorithms suggests its actual geometry is likely more irregular, possibly elongated or somewhat flattened along particular directions, consistent with the general expectation that real voids, shaped by the uneven gravitational pull of the specific filaments and walls surrounding them, rarely form perfect spheres. Pinning down the void's precise geometry matters because shape affects several of the void's other measured properties, including its total volume, its overall mass deficit relative to the cosmic average, and the predictions various theoretical models make about how quickly it should continue growing into the future. A second open question concerns the void's precise relationship to its surrounding large-scale structure. While the loose filament of galaxies running through its interior is well documented, the exact way this internal structure connects to the denser walls and filaments forming the void's outer boundary remains only partially mapped, largely because the galaxies tracing these fainter connecting structures are, almost by definition, difficult to detect using current survey technology. Improved sensitivity from next-generation instruments, particularly those capable of detecting fainter galaxies across wider fields of view, should help complete this picture considerably over the coming decade, offering a more complete three-dimensional model of exactly how the Boötes void connects to the broader cosmic web surrounding it, rather than treating it as an isolated structure floating independently in space. A third, and perhaps most consequential open question, concerns statistical significance on the largest scales. Determining with confidence whether the Boötes void represents a rare but statistically unremarkable outcome of standard cosmology, or a genuine 3 or 4 standard deviation anomaly worth taking as a serious hint of new physics, requires an accurately calibrated understanding of exactly how often voids of comparable size and depth should occur across the entire observable universe. a number that depends sensitively on the precise cosmological parameters used in the underlying simulations, parameters that are themselves still being refined through ongoing missions like the Dark Energy Spectroscopic Instrument and Euclid. As these parameters continue to be measured with ever greater precision over the coming years, the statistical case surrounding the Boötes void, currently understood as compatible with, though sitting at the extreme edge of, standard cosmological predictions, will itself continue to sharpen, potentially moving more comfortably into the range of expected outcomes, or alternatively, becoming increasingly difficult to reconcile with the standard model as measurement precision improves. Either direction would represent a meaningful and genuinely informative scientific result, and resolving this particular question stands as one of the clearest, most concrete goals guiding the next decade of research into this remarkable pocket of near emptiness. There is a certain irony worth appreciating in how this entire body of research began, an irony that says something meaningful about the way scientific discovery often actually unfolds. Robert Kirshner and his colleagues were not setting out in 1981 to find the largest empty region of space then known. They were conducting a fairly routine redshift survey, methodically working through a patch of sky as part of a broader effort to map galaxy distribution in 3 dimensions, expecting to find results broadly consistent with what had already been observed elsewhere. The void announced itself not through some dramatic signal or anomalous reading, but through a persistent, almost mundane absence. Survey after survey coming back with far fewer galaxies than expected in one particular direction, until the pattern became too consistent to dismiss as a fluke of small sample statistics. Some of the most consequential discoveries in the history of astronomy have arrived this way, not through a sudden singular eureka moment, but through the slow accumulation of an anomaly that simply refuses to go away no matter how carefully researchers check their instruments, their calibrations, and their assumptions. The discovery of the accelerating expansion of the universe itself, later recognized with a Nobel Prize, emerged from a similarly patient process. Supernova observations that consistently came back slightly dimmer than expected, under the standard cosmological assumptions of the time, until the anomaly became too robust to explain away as measurement error, eventually forcing the recognition that dark energy had to be real. The Boötes void's own story followed a comparable arc, an unexpected gap in the data that persisted through repeated scrutiny until it earned recognition as a genuine, significant feature of the universe, rather than a statistical fluke destined to disappear with more data. This pattern offers a useful, more general lesson about how to evaluate extraordinary-sounding claims in astronomy and cosmology more broadly, one that applies just as well to future discoveries as it does to the void discussed throughout this documentary. The most durable, scientifically significant discoveries tend to survive exactly the kind of process the Boötes void has been subjected to for more than 4 decades now. Repeated independent observation using different instruments and different research teams, rigorous statistical testing against the predictions of existing theory, and an honest, ongoing willingness among researchers to revise their conclusions as better data becomes available, rather than clinging to an initial dramatic interpretation simply because it makes for a more compelling story. Claims that cannot survive this kind of sustained scrutiny, including some of the more exotic explanations occasionally proposed for the void's existence, tend to quietly fade from serious scientific discussion once better evidence becomes available, while explanations grounded in testable, falsifiable physics, however less dramatic they might initially sound, tend to accumulate supporting evidence over time and gradually earn their place within the accepted scientific picture. The Boötes void's 40-year journey from startling anomaly to well-characterized, if still only partially understood, feature of the cosmic web is a genuinely good example of this process working exactly as intended. Taken as a whole, the story of the Boötes void offers something increasingly rare in popular discussions of frontier science, a genuine, still unfolding mystery that does not require exaggeration to remain compelling. The void is real, its scale is genuinely staggering, and the questions it raises connect directly to some of the deepest unresolved problems in modern physics. The nature of dark matter, the behavior of dark energy across cosmic time, the fine details of cosmic inflation, and even the long-term fate of the observable universe itself. None of that requires inventing crises that do not exist, or reaching for explanations involving colliding universes or advanced civilizations capable of engineering feats no known physics could support. The genuine science, patiently assembled across more than 4 decades of careful observation, simulation, and theoretical work, is already remarkable enough on its own terms. What comes next for this particular patch of near emptiness in the constellation? Boötes will depend largely on the results emerging from the current generation of deep sky surveys now underway, and the next generation already being planned and constructed. As instruments grow more sensitive to fainter galaxies, as simulations grow more detailed in their treatment of both dark matter and ordinary gas physics, and as statistical techniques for comparing observed voids against theoretical predictions continue to mature, the picture of exactly how extreme and exactly how well explained this void truly is will continue to sharpen. It may turn out in the end that the Boötes void is exactly what current models predict it should be, an unusually large but ultimately unremarkable statistical outcome of billions of years of ordinary gravitational structure formation. Or it may turn out to hold a genuine surprise, some subtle discrepancy between prediction and observation, significant enough to nudge cosmology toward a meaningful revision of one of its foundational assumptions. Either outcome would represent real scientific progress, and either outcome would be worth the wait. For now, the void remains exactly what it has been since 1981, an enormous, mostly quiet stretch of space, 300 million light-years across, holding a scattering of isolated galaxies drifting slowly through darkness, and holding, alongside them, one of the more productive and genuinely open questions left in the study of the universe's largest structures. Somewhere out past the herdsman, the emptiness is still being measured, still being modeled, and still, after more than 40 years, still being understood a little better with each new generation of telescopes pointed carefully into the dark.